So these are the basics for a neural network. One can create neural networks that are a little more complicated than this. For example, one could say that two weight matrices are actually tied together so that they have the same value. So, W1 and W3 might be tied together. That provides a little. The computation here of the output is very simple, just that the calculations of the gradients change somewhat. These calculations of gradients, by the way, as a preview, are really just a matter of going ahead and using the chain rule. Plus, we have so many different gradients to compute, right? We're trying to compute the partial derivative of L with respect to every single weight matrix component. So some Wi at, whatever the particular entry is, I comma j or j comma k. So we've got lots and lots of such gradients to produce. Or to calculate. So we're going to go ahead and the idea of dynamic programming, and that is going to give something that actually has the name backpropagation. But that's a preview. We will get to that. Neural networks are often presented in a pictorial form, and it's important to know how to understand that pictorial form. So we've got our x's, which here we're representing in vector form, and they're going to actually come in separately. So we'll have, let's say, an x1, x2 coming in. And then these come into what are called nodes, or sometimes neurons. And we have a connection between x1. So this is one layer, and this is to the next layer. So consider this kind of as a layer 0, and then x2. And we label each of the connections with a weight. So this might be, let's say, A1, A2, A3, and A4. And we define in each of those neurons a B. B, by the way, stands for bias, which just adjusts things. Right? The reason we have the bias is because otherwise, if our incoming X is all zeros, then Z sub I is guaranteed to be 0. Right? So by having a non-zero B, we can go ahead and ensure that even if our incoming x's are zeros, that our z will not be 0. So in any case, what do we do? Well, what this left half of a node does is, let's expand this. So we're going to make this bigger. So we go ahead and sum together input times weight. And then we add B. So this is going to be calculating x1a1 plus x2a3 plus b1. And this one is going to be computing x1a2 plus x2a4 plus b2. And then we go ahead and apply g sub 1, which often, as we've talked about, is going to be a ReLU. But let's look at this part of it right here. So we have our node consists of basically applying, doing our weighted sum, and then applying our activation function, doing our weighted sum, and applying the activation function. So often you might see this just as a sigma, right? To show the left-hand side is a sigma because that's the weighted sum, and the right-hand side is our activation function. Let's look at what's coming out of here, right? What we got out of here, so since we have two nodes here, that means the output at this layer is of size 2. So the output's of size 2, so we have 2 inputs and 2 outputs. Let's look at back sort of in matrix form, okay, as we're accustomed to. So this is equivalent to saying x1 x2 times the 2 by 2 matrix, 2 rows because we have 2 inputs, and 2 columns because we have 2 outputs. So it's x1 times a1 plus x2 a3 and x1 a2 plus x2 a4, and then we add in b1 and b2. So what we do in this picture is just unroll the entire matrix multiplication. To my mind, in some ways, we're really obscuring it. We can extend this diagram to more layers. So this is layer 1. We can look at, let's say, layer 2 might have 3, be of size 3. Sigma here, we have a G, 2. And now we again have to connect. And then we'd have to write down that we have 6 weights. And the general form of these weights is confusing. So we might view this as, let's see, this is W, the second layer, from the first node to the first node. So it might be W1, 1. And this one might be W2, 1, 2. And W2, 1, 3. And W2, 1, 1. W2, 1, 2. W2, 1, 3. Boy, certainly easier, right? We have even these subscripts that say kind of a row and column. Wouldn't it be easier to just put those into a matrix to represent that? And this, maybe this is our output, right? So we have an input layer, we have an output layer, we have no hidden layers. That, you know, could work. Maybe this is, maybe G2 is softmax. Right? And so what we're coming out with is our y hat 1, y hat 2, and y hat 3, and this would be probabilities that sum to 1. These diagrams get quite unwieldy as you get too deep. And of course, as you get the size too big, right? Again, the size of layer W sub I is just S sub I minus 1 times S sub I. So this is considered the size of layer I. And that's exactly equivalent to the number of nodes in that layer. So here, the size is 2 for layer 1, and this is layer 2, and the size is 3. So we'll not normally be using these diagrams. These were handy in the past, you know, originally when people were working with neural networks, because we could only handle very small networks, both because of computational resources and also we didn't know how to train them. So we did not have deep networks, and we didn't also have networks where layers were of particularly large size, so we could afford to look at it this way. And the other reason is these nodes were inspired by the brain, where we were looking at neurons, and so they were called perceptrons. And the focus really was on individual nodes and how you could kind of put them together, but not this larger set matrix multiplication. The matrix multiplication approach, by the way, is how it's actually implemented, right? So we work with these matrices.